while we were at ISSCC, Microsoft announced the Majorana quantum computing chip. This has been creating some amount of headlines, let me tell you.
Quantum computing, broad strokes, a potential future for acceleration of certain workloads. Just like the GPU is today, just like the NPU is about to, if we can get it to work, it will provide a massively parallel system for certain types of workloads. It won't be the thing that replaces CPUs and GPUs. It won't do graphics.
Wait, so I can't get this from a gaming rig?
Not unless your gaming rig's in a millikelvin room.
In an MRI machine.
Boring.
Boring, yes. Though you may be able to crystallize one and put it in your watch or something. It won't do anything. It just look pretty. And I'll be fair, Microsoft has made it look pretty.
Yeah. Why would they make it look so pretty?
Because it's a marketing push.
Yeah.
Okay.
And this is one of the criticisms. So just to back up a little bit, the big thing in quantum computing is, one, how many quantum bits or qubits do you have? Two, how long they last for, their coherency time. And then after that, what can you run on them that makes sense? And the research in this field, it's been going on for 20 years, but more recently, we've been tackling all three of those concurrently. For those of you who do watch the channel, one of my clients is IBM's quantum division. So I have done some content with them about their strategy. And it's the one that's actually one of the most open. They're actually getting revenue out of it by offering cloud instances. And they have somewhere north of 2,800 papers now showcasing the latest research, not only in developing quantum systems, but also the stuff that you can run on them. They've had a few papers in Nature, things to do with what can be loosely described as two-dimensional magnetic models, which is really difficult mathematically, but easier in the quantum side. 2D transverse Ising models, if you know what they are.
No idea.
I did a lot of research into condensing down does that mean, and I came to the conclusion it's when you flip a magnetic bit, it has effects in 2 dimensions, and it's difficult to model.
Oh, okay.
Due to electroweak and stuff. Turns out quantum computers are really good at simulating quantum computers.
Wow, who would have thought?
Which is Google's benchmark. I have a rant about that.
Yes,
and
you rented on it on the Tech Boutique before.
This is the headline: 17 septillion years on one of today's fastest supercomputers. Now, this announcement, this is an example of a team that has done really, really good work, but the messaging is really, really, because that number doesn't mean anything to anyone outside of this space. Arguably inside this space, it means all.
Yeah, so this is Microsoft. I misread this. I thought it said Microsoft Marijuana one, and I'm not the only one.
Microsoft releases Marijuana 1.
Yes. For those of you who don't know, Majorana is a name of the researcher in the 1800s, I believe, who has a strong connection, or has a connection, maybe it's a weak connection, electroweak connection, related to what they're doing. Now, I'm going to hand it over to George because he's a physicist.
So
now a physicist.
So
you're a space physicist, not a quantum physicist.
Well, so I have my bachelor's in physics, but this is very much into the quantum field theory. I am not a quantum field theorist.
But we know people who are.
Yeah. So if I do get anything wrong, I do apologize. I'm trying my best here. But so I'll just read the press release for the first 2 paragraphs here. Microsoft today introduces the Majorana 1.
You almost said Marijuana 1.
Yes, I did. The world's first quantum chip powered by a new topological core architecture that it expects will realize quantum computers capable of solving meaningful industrial scale problems in years, not decades. It leverages the world's first topoconductor, a breakthrough type of material which can observe and control Majorana particles to produce more reliable and scalable qubits, which are the building blocks for quantum computers.
This press release has changed since yesterday.
Has it?
Yes.
Oh, interesting. Okay.
For the reasons that we'll go into. But.
Okay. So
what it originally said is that we have multiple states of matter: solid, liquid, gas, maybe even a supercritical fluid or two.
Higgs boson go burr.
We have discovered another, a topological topological conductor,
topoconductor,
called a topoconductor, theorized by the physicist named Majorana. To which at that point, both George and I, and apologies in advance, said, "What the?"
Yeah, this is very obviously marketing here, and it's.
So explain what a Majorana particle is and why it's relevant here.
So a Majorana particle, as best as I understand it, is a particle that's also its antiparticle. So
what does that mean?
In matter, there's, if you've taken a physics or a chemistry course, then you would know what electrons or positrons, photon, neutrinos,
bosons,
bosons. These are
elementary particles.
Yep.
And most of them, as far as we know, have their own antiparticle, which means that if they come in contact, they annihilate each other because it's essentially a positive and a negative coming together.
Yes. So traditionally, there's the electron, the neutron, and the proton. Probably the one that you've heard the most about before is the positron, which is the antimatter version of the electron. If they come in contact, they annihilate each other, which is why a Majorana particle is weird, because it's both a particle and it's antiparticle. So
the problem is they don't exist.
Yeah, they don't exist. Now,
they're theorized to exist in certain theoretical fields of physics.
Yeah, mostly in ultra high energy systems.
Imagine like super Higgs bosons.
Yeah.
The reason why they've called it the Majorana is because they believe they have created the equivalent of a Majorana fermion in the form of a particle at the end of the nanowire. Now, kudos to them if they have. They said it's got the same properties. They've had to do a bunch of design work to get it to work. Apparently, this has been in work 17 years.
So this is not a Majorana particle. What this is it
exhibits the same properties.
Yes. So essentially, what you have, you explained it as an eaglet, and I actually really like that.
What they've taken is a nanowire, and they've reconstructed the end of the nanowire atom by atom to have specific properties. I think it was indium, gallium arsenide or something. I went over the paper yesterday. But if you construct it in a certain way, put it into what's called a quantum well, which means that you're essentially lowering...
you're forcing it into essentially a place where
a lower quantum state.
Yeah, you're forcing it into a specific quantum state within a well.
Yeah, and then you cool it down to, as George said, millikelvin. And do they also have to apply an electrical field, or they have to apply microwave pulses to program it anyway? If you put two of them together, it creates a Dirac fermion equivalent, which is like a particle-antiparticle situation.
And these are two quasi-particles at the end of those wires that have been formed.
But you put four of them together.
Yeah, you put two. Well, no, you put two of them together and you get a Dirac fermion. You then entangle those two with another two, and you get what they're claiming behaves like a Majorana fermion,
which can exhibit behavior such that it can be used for quantum computing.
Yes.
So that is a very long and convoluted way. Because part of the issue here is they have literally had to physically create these nanowire ends atom by atom to get it to work. The device itself, as you can see in the photos here, is 7 or 8 qubits. I believe it's 8 physical, but only 7 work or something.
Okay.
And
so quantum computers have yields just like regular computers.
it's and so you might think, for anybody who does follow the quantum computing industry, they might think, so why is this a major breakthrough? And the reason why they're considering it a breakthrough is for pretty much one reason. And it's 1.5 reasons. And it really annoys me.
Mm-hmm.
The first one is that the size of the quantum well and the end of the nanowire is really, really small.
Mm-hmm.
Therefore, on your hand, you can fit 1 million, and quantum computers in the future need 1 million qubits. So don't bother doing any quantum computing on stuff that won't scale to 1 million qubits on the palm of your hand. The thing is, that's pretty much all quantum computing qubits are. So, for example, IBM's qubits, you can scale to a few thousand on a chip that's about 4 inches long. So that won't scale to 1 million, but it's the one that's working right now.
Yep.
Intel has spin qubits, and because that's actually manufactured on a CMOS process, you can get millions out there. So this is not a bloody new concept of saying let's scale to 1 million. Not on top of that, I'm getting very ranty now because I'm pointing and banging the table. Doesn't take into account the bloody electronics to power the thing.
Yeah,
because those scale as well.
Yeah, those. Yeah, it's so.
The other half point that they're trying to make here is that I mentioned at the beginning that quantum qubits have a coherence time.
Yes.
So what you're doing is you're putting the quantum wave function in a state that you can use it for compute, and you don't want that wave function to collapse. So that's called the coherence time. And the longer your coherence time, the more you can do in the entangled state as a qubit. And this is, much research going on this. They're saying that due to the nature of their quantum wells, they exhibit 10 times better coherence time than other qubits in the field, which is a weird thing to state, given that there is research going on to other superconducting qubits to improve the coherence time by 1000x over the next 3 years.
Yeah. So it's very, if this works, this would be very interesting. However, this is not the first time we've seen this.
Is it not?
No, it's not.
Oh,
so,
this is news to me. George has done some research overnight.
Yeah. So in 2021, it's in the doc.
Okay.
I'm going to quote from the IEEE spectrum.
Okay, I'll bring this up.
Major quotations on a backpedaling, Microsoft-backed quantum computer research retracted. They've published a very similar paper before and have retracted it.
In the past decade or so, researchers have detected signs of a kind of Majorana fermion known as a Majorana zero mode. This quasi-particle manifests in the form of groups of electrons and other particles behaving as single particles. And in 2018, in Nature, Microsoft-backed scientists claimed they found strong evidence. A discovery they suggested could pave the way for the powerful kind of quantum computer. Now the researchers have officially retracted this work, citing insufficient rigor. So it sounds like they now believe they have the rigor needed.
Yes.
And they've done it. Well, hang on. This is a story in 2021.
Yeah.
Retracting a 2018 paper.
Yeah.
So
and now republishing in 25.
So 7 years later, but also to that extent, they've also built it into a quantum computer.
Yes.
And a lot of people are finding the results, I don't want to say not sufficient, or not believable, but needs more data.
Yeah, it's give me more data before I start really fanboying over this.
Yeah, because there are other types of qubits in this industry that have a long history that are in the process of yielding and working.
Yeah, and I will say that this is actually, I think this actually is the first time that a topological superconductor has been made.
Mm-hmm.
And been used in an actual use case. But a lot of people are saying it's an interesting curiosity that should be explored more, but call me when this starts scaling more and more.
So the paper is in Nature. It is open access for people to read. It gets pretty dense pretty quick. It's showing here how
and you can see, if you go back up, you can see how
four ends of a shoelace.
Yeah, basically.
How they're connected together. So yeah, if you don't know the end of a shoelace, the little plastic cover is called an iglet. So they could have called it Majorana. They could have called it the Microsoft iglet. But
The iglet computer.
Yeah, so a lot of people were annoyed, were like show the data.
Mm-hmm.
A lot of people said this is a lot of marketing bunk.
Yeah, here I don't know if you showed that paper, but there's also a paper on what exactly is topological superconductor is.
Yeah.
Better than MS telomere. Yeah. But yeah, it's very interesting. Expect to see more talk about this as more data comes out about it.
Yeah, that's the other thing we should highlight, which was actually brought up to us by a good friend in the room here. One of the key things in the press release is that after this demonstration, this has now unlocked the final stage of a Darpa research program to build one of these supercomputers for what looks like potential military use.
Okay. Well, yeah, that's Darpa for you. But
yeah, so this is part of the Microsoft Azure blog. One of their things is reliably reading quantum information as well.
Yeah. And something.
So hang on. Let's let me. So they've got a bunch of research labs. As a result of this careful analysis, DARPA and Microsoft have executed an agreement to begin the final stage of this program. During this phase, Microsoft intends to build a fault-tolerant prototype based on topological qubits in years, not decades.
Yeah.
If this is as big as they say, there would be a lot more than DARPA getting involved for a start.
Yeah. Well, there is one other part that I would like to bring up, and that's in the paper they talk about fault-tolerant computation.
Mm-hmm.
So if you guys know in classical computing, there's ECC for memory or error correcting code.
Mm-hmm.
For DRAM sticks, NAND, whatever else.
SecDed, TechSec.
Yeah. What's really interesting is that a topological superconductor sort of can have what inbuilt ECC by having a band gap between the quantum states. So a band gap is a difference in energy potential. By having this band gap between the different states, essentially where you are in that quantum well that we talked about, you can have a better fault tolerance, which is really important for quantum computing, because that's one of the things that a lot of research has gone into, is how do you better make a less faulty or more fault tolerant system.
Mm-hmm. I want to show this picture. This is how you make your Majorana zero mode.
Oh, this is the MZMs. So
it's a squiggle.
Well,
so some lines are dotted, some are fuzzy.
Yeah. So Majorana zero modes are a specific zero energy, is a certain state of the system, essentially. So you can tangle or you can couple 2 or 4 of these zero modes together to protect essentially the state of the electron that you're using to. So what's funny is, because this is quantum, when you capture the electron and it becomes coupled to the MZM system, the state then becomes unobservable. Yeah, it's very interesting on how you would measure it.
There's still a lot of questions, let's put it that way, and I've had people reach out saying, what does this mean? Is this real? The fact that Microsoft's putting so much noise behind it.
Yeah.
And to be honest, I think that's the biggest gripe. I mean, the initial gripe that covers everyone is how much effort they're putting into marketing it. The second biggest gripe is physics.
Yeah. And somebody in the chat says, because if you measure it, you change its state, messing up your computation. That's yes, but that's not. It becomes like you can't observe it because of the zero modes. It's weird. But you can get a measurement out of it, but you can't observe it. But
some of the way these things work is you observe the effect it has on
Yes,
something else.
that's exactly what
so
it is.
so you don't collapse its own wave function, you're collapsing the wave function of something else
Yeah.
by looking at the interaction.
Which-
So it's a proxy calculation.